On December 1st, 1990, two engineers met deep beneath the English Channel.
There's the handshake we've all been waiting for, Mr. Defag and Mr. Cosette.
45 meters below the seabed. Reaching through a small opening in the rock, they shook hands. It was the moment Britain stopped being an island. For the first time since the last ice age, nearly 8,000 years ago, Great Britain was physically connected to mainland Europe.
The Channel Tunnel.
Tunnel.
Disruption in the Channel Tunnel.
But that handshake almost never happened. The Channel Tunnel cost nearly $15 billion, pushed engineering to its limits, and nearly collapsed several times before completion. For more than a century, experts believed a tunnel under the English Channel simply could not be built. Yet today, more than 30 years later, this massive project is entering a new phase. In 2026, new technology upgrades are transforming the tunnel into one of the most advanced rail corridors in Europe. This is the story of the Channel Tunnel, the billion-dollar plan engineers once believed would never work. Please take a moment to subscribe and like the video. It really helps the channel. The idea of a fixed link between Britain and France is not new. Engineers first proposed tunnels under the English Channel in the early 1800s. Some early designs imagined horse-drawn carriages traveling through tunnels, lit by oil lamps. Others suggested huge artificial islands connected by bridges. But the English Channel is one of the most difficult places in the world to build anything. It is one of the busiest shipping routes on Earth. The water is deep, the currents are strong, and for many years the geology beneath the seabed was poorly understood. Because of this, every proposal failed. Sometimes the cost was simply too high. Other times the problem was political. Many British leaders feared that a tunnel might make it easier for enemies to invade the country. But by the 1980s, the situation had changed. Trade between Britain and Europe was growing quickly. Ferries and cargo ships were no longer enough to move people and goods efficiently. If Europe wanted stronger economic links, the water between London and Paris had to be crossed in a faster and more reliable way. Still, the British and French governments made one rule very clear. Not a single penny of public money would be used. Private investors would have to take all the financial risk. It would become one of the largest private infrastructure bets in history. The company chosen to build the project was Eurotunnel, and the plan they proposed was incredibly complex. Engineers were not building just one tunnel beneath the sea. They were building three. Two large outer tunnels, each about 7.6 meters wide, would carry trains in opposite directions. Between them would be a smaller service tunnel, about 4.8 meters wide. This central tunnel would act as the system's safety and maintenance corridor. It would provide ventilation, emergency access, and a safe place for workers if something went wrong. But first, engineers had to find the safest path through the ground. After years of geological studies, they chose a layer of rock called chalk marl. This rock layer sits about 40 meters below the seabed. It is soft enough to dig through but strong enough to hold its shape. Most importantly, it blocks water very well. If the tunnel stayed inside this layer, it would remain dry. If it moved too high or too low, the machines could hit cracked rock or sand, allowing seawater to rush inside. And under the English Channel, that would be catastrophic. To dig the tunnels, engineers used 11 massive tunnel boring machines, often called TBMs. These machines were enormous. Each one weighed around 1,100 tons and stretched longer than 2 football fields. Imagine a machine that large, slowly crawling through the earth, cutting rock while building a tunnel behind it. As each TBM moved forward, it installed strong concrete rings to support the tunnel walls. In total, more than 750,000 concrete segments were used during construction. These segments were designed to last at least 120 years. But digging a tunnel creates another problem. What do you do with millions of tons of excavated rock? In England alone, the project removed almost 5 million cubic meters of material. Instead of dumping it elsewhere, engineers used the rock to create Samphire Hoe, a completely new 90-acre piece of coastline at the base of the White Cliffs of Dover. It is literally land made from the bottom of the sea. When the work was finished, the British TBMs faced a strange problem. They were simply too large to remove from the tunnel. So engineers drove the machines deeper underground and sealed them in concrete. Today, those giant machines are still there, buried beneath the seabed. The most stressful moment of the entire project was when the two sides had to meet. The British team started digging from Shakespeare Cliff near Dover. The French team began from Sangatte near Calais. Both sides drilled toward each other through darkness, deep beneath the seabed. Even a small mistake in direction could cause the tunnels to miss each other entirely. To stay on course, engineers used advanced satellite positioning and laser guidance systems. But the margin for error was incredibly small. After years of drilling, the moment finally came. In December 1990, the pilot tunnel broke through the final wall of rock. When engineers checked the alignment, they discovered something remarkable. The two tunnels were off by only 35 centimeters. For a project drilled from two different countries beneath the sea, this level of accuracy was almost unbelievable. It proved that the centuries-old doubts about the tunnel had finally been overcome. The Channel Tunnel officially opened in 1994, but building it was only the beginning. More than 30 years later, the project is entering a new phase. Today, the tunnel is being transformed into a smart tunnel. A major upgrade is installing the European Rail Traffic Management System, also known as ERTMS. This advanced signaling technology allows trains to travel closer together while maintaining high safety standards. As a result, more trains will be able to pass through the tunnel each day, without building any new tunnels. The power system is also being improved. A new electrical technology called STATCOM helps stabilize the power supply for high-speed trains, ensuring smoother and more reliable operation. The tunnel is also becoming part of a greener transport network. In early 2026, pilot programs began testing electric heavy goods vehicles traveling through the tunnel. The goal is to create a low-emission freight corridor between the UK and mainland Europe. New freight connections are also being developed through logistics hubs like Barking in East London. Today, the Channel Tunnel remains one of the most impressive transport links ever built. The entire system stretches 50.4 kilometers, with 37.9 kilometers running beneath the sea, the longest undersea section of any rail tunnel in the world. Financially, the project is finally stabilized after many difficult years. The tunnel's operator, Getlink, reported earnings of €859 million in 2025, with long-term goals of reaching €1 billion annually by 2030. But the story of the tunnel is still unfolding. Plans are moving forward to create direct high-speed rail connections from London to cities such as Cologne, Geneva, and Milan. Italy's National Railway is even planning new train services between Paris and the United Kingdom by 2029. The Channel Tunnel was not just a construction project. It was a test of engineering skill, political cooperation, and financial courage. For more than a century, people believed the English Channel was a barrier that could not be crossed underground. But in the end, engineers proved something remarkable. Sometimes the greatest bridges are not built above the water. They are built beneath it.